Okay, welcome back. We're in a reduced setting, in a smaller setting today. Okay, so we are recording now. I'm sharing my screen. So I have not decided that Wednesday next week we're not going to do class. So go off on your holiday and. Okay. Well, you're traveling. It doesn't really make sense. And we're in a good pace. We're in a good pace. Okay, but we're.
You know, I wish I could go, but I'm not flying 7 hours. Where do you live? Amsterdam. Whoa, yeah.
Yes, not around the corner. I love Amsterdam. Don't. It's one of my favorite cities in Europe. Amsterdam, beautiful city.
Have you ever been to Hungary?
Hungary?
Yeah.
Yes.
My parents are from there.
Oh, really?
He knows that. I often have that state. Yeah, hunger.
And from where? Do you know where?
What?
Do you know where?
I know what. Where? Oh, my dad's from Budapest.
Budapest. Okay.
Yeah. Well,
Beautiful.
I speak Hungarian.
You speak Hungarian. Very nice.
I was supposed to go to Budapest.
My mother speaks Hungarian too, so I have some Hungarian roots too.
Yeah. You understand it?
No.
Speak to each other.
That's a very fascinating language. It's actually not really. It's not a Latin language. It's different from all the other European languages. It's actually more inspired by Scandinavian dialect or Scandinavian languages. A very fascinating language.
My parents speak like different slangs.
Yeah.
My mom's from the countryside. My dad's from the city.
That's nice. Fascinating.
Yeah.
Yes.
Have you ever been to Israel?
No, that's still on my list.
Yeah.
Still on my list.
What country?
So, okay, so no class on Wednesday. We're doing today module 16, which is the independent sample t-test. It's chapter 11 in your books. And yeah, concerning syllabus, I think we talked about it last time. So we're talking now about the independent sample t-test. Next week, Monday, we're talking about t-test again. We're reviewing all the 3 t-tests we've discussed because that's a very central topic. So you're also going to have practice lab 3 coming out. This is going to be due on the Sunday. So you're going to have, yes, but it's a practice lab, right? So
That's this Sunday.
no, that's the 28th. So that's after Thanksgiving and everything is over. Yep. Good. And then on Monday, then we're going to go spicy again. We're going to have ANOVA. We're reviewing it on the Wednesday and then digging into correlation and linear regression. And then we do an overarching lab day where we repeat all these exercises. Good. Homework 2 also comes out then. Homework 2 is going to be mainly on t-tests. It's going to be a lot of calculations. So it's going to be a lot of calculations. Don't forget, I want the calculations, right? Good. Okay, independent sample t-test. Just like discussed last time. Last time we looked into the differences within groups when you have repeated measurements within individuals. Today, we're going to be talking about the comparison of 2 means in a between group setting. So we have independent samples. We have 2 different sample populations that are different in the means, or at least we hypothesize they're different in the means. With another hypothesis that there's no difference between these means. So it provides a situation in which each participant is assigned to only one condition. So this is the setting of a randomized controlled trial. A randomized controlled trial that is really balanced at start, at randomization time point, hypothetically, you could calculate that treatment effect of the intervention using a simple t-test, a simple independent samples t-test. And so now we have with the paired sample t-test, we have compared the mean differences, right? We have looked at this difference of these different differences. We have drawn samples of differences from our list of differences, from all these calculated differences, and we have built our distribution of the mean difference. And we have used that for hypothesis testing versus a change of 0, where there was no change in the condition before and after. This time around, we're looking at the distribution of differences between means. So now we're grabbing different samples. So we have those two sample populations. We're grabbing different small little samples from our sample population. We're building means, and we're getting mean pairs. And these mean pairs have differences. And these mean pairs, the randomly sampled mean pairs, essentially build our distribution of the differences between the means, between these randomly sampled means. And this is this distribution that you see here. So here's the example of the happiness scores, and this is an example that we will do for the lab. So we essentially, again, two sample populations. We're drawing little samples out of the sample populations. We're calculating differences between those, and we get randomly sampled differences from these randomly sampled subsamples. The mean differences between two samples of happiness scores are depicted here. And the null hypothesis that these means between those two sample means do not differ from each other. So the steps for hypothesis testing are once again the same as they always are. We identify the populations, the distributions, and the assumptions. What's happening now? Okay. So I am recording good. So we're identifying populations, distributions, and assumptions. We state null and research hypothesis with determining characteristics of the comparison distribution. We determine critical cutoffs and the critical values. We're calculating the test statistic and make a decision. So how are we doing this? So now let's assume that example that Norton and Heinzen have put forward. So you take bottles of wine, and you have people drink this wine and taste this wine and rate this wine. So now let's assume the population one, you're telling them this is a really cheap wine, this is a $10 bottle of wine. The other population, you're telling them, okay, so this is a really top-notch wine, this is a $90 bottle of wine. The hypothesis is that people will rate the wine based on the price tag they're communicated about this wine, which is sad but true, unfortunately often true. The distribution is now a distribution of the differences between the means. So you take these little samples out there, you get differences between the means, and you sample and you look at the distribution of these means, rather than the distribution of the mean differences. The mean differences are these differences that we calculated last time, right? Individual scores, and we get differences between these individual scores before and after. This time around, we get means, randomly picked means, and we get these random differences. And based on that, we're building a distribution of these of these differences in means. So assumptions are, as always, participants were likely not randomly selected, so we must be cautious with respect to generalization. We don't know whether the population is normally distributed. Given the small sample size, likely they're not, but we assume we get away with it.
We're still talking about a t-test, right? We're still talking about the t-test?
We are.
Okay.
And this is the overview. So this is where the money is.
Okay.
So you have a set test. You have one sample, and you know it's a normal distribution. It's from a population, and you have a distribution of the means, right? You have random samples from a population that you draw, and you get a distribution of means that you compare to the population mean. Then you have a single sample t-test. Again, you have a distribution of the means. You have one sample, and you're comparing these random picked samples and the distribution of the means. but you're estimating now the distribution based on the standard deviation that comes from the sample population. This is the n-1 for the standard deviation calculation. It's not the sample size like it is for the set test. So these are kind of the tricky parts where a lot of mistakes have been made. Single sample t-test, you estimate the standard deviation from your sample. That will be the trigger for you to use a one sample t-test. Paired sample t-test, you have a before and after condition. And you have mean difference scores for each individual, for each participant in your study. And you get a difference from a before and after condition. Independent sample t-test, now you get a distribution of the differences between the means. So you have two samples, you draw from both samples, you get from these randomly drawn samples, you get means, and you calculate the difference between the means. And the distribution you use for hypothesis testing is the distribution of the difference between the means. It sounds like a subtle difference, but it's conceptually, let that sink in. It's conceptually, it's a huge difference. Okay, good. And you have two samples. Two samples you have for paired sample t-test and for independent sample t-test. But the concept is different, which makes a difference because they're calculated entirely different, because you need to employ some certain principles to account for the sample size. Because you will see, you will see, you will see, you will see. Trust me, trust me for now. All right, null hypothesis. Both populations, whether they're being told it's a $10 bottle or $90 bottle, will have the same rating. That's the null hypothesis. Two-tailed test. On average, people drinking wine are told it's from a $10 bottle compared to the $90 bottle. They will rate the wine differently. That's the research hypothesis. So now again, you do the 5 stages. Okay, so it's more complicated to calculate the measure of spread. And this is really the problem. So calculating the mean difference is not complicated, obviously. But what's different is the variability or the variance for these samples. Because you need to take into account that the variance is different for each sample, depending on the sample size. So I could read this to you, which doesn't make any sense. I show it to you. And we're going to calculate it later too for repetitive kind of didactic value. So first, we're calculating here the variance. We're calculating the variance just like we always did. We are subtracting the individual score. So 2 sample populations. Each individual scores, you subtract the mean from each individual score, you square it, you get to the standard deviation. You don't employ the square root yet because you need the variance for now. You calculate the variance for both samples. In the next step, so you get these 2 sample variances. In the next step, you build what is called a pooled variance. And now it's getting tricky. Because, because the pooled variance, do you know what an aliquot is? An aliquot distribution according to the sample size in the sample population. So if you're calculating, we talked about proportions, right? So you have the degrees of freedom of your sample X divided by the degrees of freedom in the total population in both samples together. So for the wine drinkers, the example is 8. So degrees of freedom is 6. And you have, in one group, you have 4. So the degrees of freedom for X would be 3. So you have 3 divided by 6. So you get an aliquot. So you assign a part of this variance, of this variability, to each of your samples. So you balance it out according to both population, according to the size of the population in proportion to the overall population of both samples. Everybody with me? No? Okay. Okay. Take it and let it sink in for now like this. By that, you're creating of your variance for sample X. You create a variance for sample X, which is assigned to that's the weight. That's the weight on sample X based on the sample size in sample X. You do the same for sample Y, and you assign again an aliquot based on the proportion that sample Y is contributing to the overall weight to the variance of Y. Then you take these two, so that gives you the standard deviation or the variance for X and the variance for Y. So you have two variances. These variances you divide now by the sample size, and by that you get to the standard error of the mean. And that is the tricky part.
Why is that?
Because as soon as you have the variance of the mean, as soon as you have the standard error of the means for both samples, you just sum them up. You employ the square root, and you get your standard error of the mean. And from that point on, it's business as usual. You have the differences, and you're basically getting now to your t-square by dividing by the standard error of the mean. And you're subtracting here the null hypothesis, which is here 0, because you assume that there's no difference between those two samples. So this is your final formula. This is mx, that's the mean of population X, minus the mean of population Y, divided by the standard error of the mean that you calculated here that overly complex way. Yes?
Can you show us a problem using numbers, please?
Yes. That's just the principle for now. We're calculating through this too. Okay, so far so good. Okay, then with the t, you do the hypothesis testing, business as usual. Okay, so now we're gonna go calculate this. So let's complete the example. Looks worse than it is. Okay, we have here, zooming in. So we have here, and this should be on canvas. You should have this on canvas. Can you confirm it's the same on canvas? Yep. Good. Okay, so you have the $10 wine. You have here a rating of 1.5, whatever that rating is. 1.5, 2.3, 2.8, 3.4. You have 2.9, 3.5, 3.5, 4.9, 5.2. To make it more of a realistic example, they actually have chosen to take unequal numbers.
Why?
Because that's what you will face in real life. So it accounts for differences in the variances for each sample. Because that's where the aliquot essentially does suddenly become a lot of weight, and it becomes obvious why there is an aliquot assigned to each variance. Okay, so you get an average of 2.5 for the $10 wine, and you get 4 for the $90 wine. So I have transposed this here already, and here it's basically it's business as usual. Bring it over there. Calculate the x minus m, which is here this minus this. We're doing the same for this. We're doing x minus m. It's this minus dollar this. So that's dollar H dollar 3. Dollar H dollar 3. So this is your formula. Now we do the x minus m squared, gives us the squared deviations. That's squared. And the same here. So far, so good, right? This is essentially the same thing we always do. Squaring this. So what are we doing next? So now we have the variances. So now we need, so let's go back here. We are currently here. We have summed that up, we have squared that. We're dividing that now by the n minus 1. So this is the variance x. It's actually y minus m. Sorry. Let's label it right, then it's less confusing. Okay, so variance of x equals this divided by count of this minus 1, right? No. Oh. Sum L6 to L1. Oh boy. Tell me get my good chances back. Okay. Okay, sum x to sum 9 divided by count L6 to L9 minus 1. This is 0.65. Okay, so we're summing up the squared different deviations. We're dividing it by count L6 to L9. That's just counting 1, 2, 3, 4, minus 1. We just need 2 parentheses if you use this formula.
Okay, y minus 1.
Because it's a sample, right?
Oh, so and then.
It's degrees of freedom. It's not the sample size. The sample size would be only with set statistic. Whenever you calculate the standard deviation from a sample, you would use n minus 1.
Can you go over the formula?
Hmm?
Can you go over the formula?
The formula is right here.
But how can I do that on Excel?
That formula is what? Do it here with y. So it's sum Q6 to Q10. So it's the sum of these Q6, Q10 divided by parentheses open count Q6 to Q10 parenthesis closed, first parenthesis closed, minus 1, second parenthesis closed.
Two parentheses in front of count.
Now just one parenthesis in front of count.
Yeah.
Count gets its own parentheses. Q6 to Q10 gives it where it should count, parenthesis closed, first one closed, minus 1, second one closed. The reason why I'm torturing you with count is because down the road, if you have larger sample sizes, it's going to be useful to use the count function. And also, if you hypothetically, if you alter your data set later on and you need to delete something from anywhere from your variable list, it will not count it because it doesn't contain a value. It only counts whatever has a value. So that may be helpful at one point. And that's what I'm trying to do. I'm anticipating what you may be exposed to down the road at one point, possibly. And that's why I'm showing you formulas that necessarily are not needed at this point, but may be helpful at one point. Okay, so these are the variances. What we're doing next. Everybody on board with the variances? Good. So now we are at this stage. Now we do this monster. So we're getting this now in the spreadsheet. Because just makes it easier. Okay. So now we're calculating these aliquots.
What is it called?
Hmm?
What is it called?
Aliquots. ALIQOTS. Aliquots X or aliquot X. So aliquots, I'm using this in the lab. If you have a sample and you use a pipette to take it out of the sample and you put it on different smaller vials, you call it aliquots of the bigger one.
What's the bigger one?
The bigger one would be, so you draw a blood sample and you spin it through in a centrifuge and then you take a pipette and you take it out and you distribute it on smaller little vials, that's called aliquots.
Putting it
In smaller ones, and you distribute it.
in. Increment?
An increment would be something that increases, right?
Decrement.
So that's state raising.
Yeah, but not it.
No, it's an aliquot. It's a part of a whole. Don't worry, don't worry, don't worry, don't worry. Let me use my terminology, look it up if you're interested in that. Okay, aliquot X, so it's a part of a bigger sample. It's a proportional part of a bigger sample. And this is essentially what it is, because if you do, so now what we're doing is dfx divided by df total. So what is df total? Df total is nothing else but count of these entries, comma, these entries, right? So we're just counting this up. And this degrees of freedom total is 9.
Which ones did you count? Square or not square?
Doesn't matter. It's just counting something that has a value. So here 4 and here 5.
You don't use like this function in Excel, if we just like count it by hand.
Yes, you can count if. You remember we did the volcanoes?
We did what?
Volcanoes, the volcano example with the frequency distribution, that's when we do count if. So you can, with count if, you can, for example, you can employ a count if function on an entire variable, like 1,000 entries, and you tell it only count those that are smaller than 5, for example. So this is where these functions are super useful. And that's why I'm torturing you with them. Okay, aliquot X is now the proportion of X is count of this divided by this, right? 0.44. So aliquot Y is now nothing else but count of this divided by 9. Right?
Just 4 divided by 9, 5 divided by 9?
So df total. Both are divided by df total. Yeah?
Isn't similar to the t-test.
Hmm?
Isn't similar to the t-test.
Well, we're getting there. We're getting there. We're getting there. We're on our way to get there. Okay. So just to make sure. So now sum of this and sum of this, what would that give?
Oh,
1.
what did you just do?
1.
1?
Yeah. This and this is 1. It's a proportion, right?
You're adding.
There's nothing else. We're calculating two proportions, aliquotly distributing it between both sample populations. And now we're doing nothing else but taking the variance that we have calculated for each of these samples. So we do a var x multiplied by this proportion. And we're doing a var y, which is this variance multiplied by this proportion. Yeah?
Wait, you multiply the aliquot by.
We're doing now this step. We're calculating dfx divided by df total, which is our 0.44, multiplied by the variance of x. And we're getting a variance for each part of our sample with that weight for that sample population in our comparison. So we're weighing it. We're giving it some, we're reducing the weight according to the sample size. It contributes to the overall sample. Yeah?
No.
No.
Why do you multiply it?
So you have variability in both sample populations, right? And you are estimating, you're randomly drawing now from both sample populations 2 samples, and you're calculating the difference between these.
Oh, but it would be so.
Yeah. Yes, and this difference in the variability of this differences in means, so this distribution of the differences in means do have a variability. And that variability, if you want to translate this to your distribution of the the differences in the means, you want to use this for your sample distribution of the differences in the means, you need to weigh it according to the sample size in the respective sample. So this is when you give it a weight. And this weight is calculated by calculating proportion and multiplying it with the variance of the respective sample. So now we have two variances. What are we doing next? We need the standard error of the mean, right? And now we're doing something that's different. Again, something that's different. So we have not a variance. What would we commonly do? We would employ the square root to the variance, get to the standard deviation, and to get to the standard error of the mean, we would divide it by the square root of the n, right? Gets us to the standard error of the mean. We're not doing that yet. Okay, that was the honest reaction. Okay, what? Like that. Okay, good. We're not doing that because we're still operating in a squared setting. If we're not in a squared setting, we can only divide it by the sample size rather than the square root of the sample size. Arithmetic 101, right? So the only thing we're doing now, we're getting now to an SEM squared. And Nolan and Heinzen, they're calling it different. They're calling it S difference. So we're now here. No, oh, sorry. We are now at this stage. We want to have this S squared difference, which is the variance of the difference, which is essentially the standard error of the mean of the differences in the means. That's the standard error of the mean you're going to be working now calculating the t-test. Okay. Okay. So yeah, and we're getting now to this guy. This is the standard error of the mean squared. So we're dividing now the variance, and this is where the trick is. And this is a little tricky, and I sympathize with you because that's a little bit of a thought process. So we have here variance of the x, and we're dividing that by the sample size. So this is again our count. And this is our standard error of the mean squared. Okay? And we're doing this at SEM, oh, that's the SEMY squared. This is this divided by count of this. 0.11, so this is SEMX. And now we are doing an S squared difference by summing this up. The sum of this and this.
We're just adding them both.
Correct. You're adding them up. And now we're getting now to this. Where we essentially do nothing else for calculating the mean difference, dividing it by the standard error of the mean. So we need to do now, so this is now S difference equals SQRT divided by this 40.3, 0.40.3. So when we want to get now to the T, we need to calculate the difference, which is given here. But let's do this here. I mean average J6, J10, and then J10. So we have now a difference here of 1.5. So our T equals X minus mean Y divided by this minus 3.51. So now we're just taking the mean from here, which is 2.5, minus the mean from here, and we're dividing it by the standard difference. The S difference is our that's broke. So the difference is now our standard error of the mean. Sure. That's the standard error of the mean, and this is being used to calculate.
I didn't get that. What's the formula?
Okay, once again, let's go through the whole thing.
Yeah.
Okay, means. Variances are calculated by each individual score minus the mean, gets us to the deviations, squaring it up gets us to the squared differences, dividing the sum of squares by n minus 1 gets us to the variance. We're not employing the square root, we're staying on the squared level. We're using an aliquot, which is basically a proportion of the sample size of sample X to the overall sample X plus Y. This proportion here is aliquot to the weight of each sample in the total sample population of both samples. Adds up to 1, is a total of 9. We're getting a variance X. Variance X is here what we calculated before. We're multiplying it by the aliquot, by the proportion. We're getting to an aliquot variance, how much variance this sample is contributing to the overall sample population. We're doing the same for Y. We're still on the squared level. That's why we do not employ the square root on the sample size, but we're only dividing it by the sample size. We're getting to standard error of the mean of X of 0.07 and the same 0.11 to the standard error of the mean squared of Y. Now we're adding it up. We're employing the square root. We get to this S difference, which is now the standard error of the mean aliquotly distributed to the weight of each of our samples. And this represents the variability of the differences in the mean distribution. So this is the standard error of the mean. So before we took means, and we assumed this is the distribution of the sample means. Then with the paired sample t-test, we used the sample so the distribution of a sample mean differences. Now we're using the distribution of the sample differences of the means. And this is because we draw independently samples, we calculate the differences, and that has a certain distribution. Okay? And once we are at that level to have this S difference, we just have to divide our difference, which is the difference of the differences, the mean difference of all these samples that we've drawn. And we're using the standard error of the mean to calculate whether it's significantly different. With a t-score of minus 3.51, would you assume this is different or not? For that, we need the t-score table. And this is the same t-score table that we always used. Here we go. We have a sample size of 9 with 2 groups. Our degrees of freedom is going to be 7 because we're subtracting 2, not 1. 1 for each sample. So now we're at 2.36, and that's our critical value. And now we have minus 3.51, which in a two-tailed test doesn't make a difference whether it's minus or not. And it exceeds the critical value. Thus, it's significantly different. Okay?
It is significant or it's not?
Hmm?
It is significant or it's not?
It is significant.
Wait, you looked at the 7 and then which column?
5%.
Why 5%?
Because we determined this before to be our critical value. So yeah, I should have determined it earlier. You're right.
Wait, I'm sorry, how did you get T again, the last step?
The what?
The last step. What did you do there?
Well, that's the difference divided by the standard error of the mean. This S difference is our standard error of the mean.
Wait, that standard difference times, I need to divide that off.
No, we're doing difference x minus y. So the mean x minus mean y divided by the standard error of the mean, which is S difference.
Two standard error, one for X and one for Y. So which one do you
No.
divide by?
No, you merge them. You sum them up.
When did we sum that?
Here.
Okay.
So you do everything. So you get here an aliquot standard error of the mean for x. Independently, you get a standard error of the mean y. And you get here a standard error of the mean of the differences squared for both. And then you employ the square root and you get to the standard error of the mean for the entire sample population of the comparison of the distribution of the differences in the sample means. Yeah. So this is what Norn and Heinzen had to say here. They have 2.44. Oh, that's interesting.
Why for the standard difference do we add 2 instead of subtracting one from the other?
Excuse me?
Why for the standard difference do we add 2 numbers instead of subtracting one from the other?
Because it's a summed distribution of the differences in the means. So you are you're estimating. So you're taking random samples from each sample, and you take these samples and you calculate the difference. You get one difference. Then you take another one. You get the second difference. So this has a certain variability, and you're weighing the variability based on each sample size. And this is where you calculate proportions and you aliquot them. Yeah?
Thank you.
Sure. But I need to double check here something because they have a different value. I'm not sure why they have a different value. I have 0.21. What did I do wrong? I did something wrong. 0.43. Ah.
Oh no, what did you wrong? Oh
It can't be good.
Wait,
Okay.
no.
So,
Oh no.
no, it's not bad. It's just when the calculation of, when you're doing the calculation here, you're not doing, this is not DF total. DF total is -2.
Tricky.
Yeah. And here it's also, here it's count -1. It's not.
Something like this wouldn't be on an exam, right?
Not in this detail, no.
But this would be on a homework?
On the homework it will be. Yeah.
I'm not sure I could do this on a homework. Well, we have this.
Well, now you have the formula, right?
What?
Now you have the formula. So here it's, so what's important here? No, I'm backwards tripping first. Hold on, what's going on here? Hold on, this is 4. 7. This is 3.7. Okay. For the 257, 784. Let's pull 784. That's a good one.
Yep. Oh no, what is happening? It's not. Yeah, I also say like online textbooks. Like I know
That is interesting. Okay. This. So we have here. Okay, so there's a little rectification I have to make. So we're coming from 3.3 divided by 7. So we have a degree of freedom of 3, right? So we have here a sample size of 4. We have a sample size of 5 here. This gives us an aliquot of 3.7 and 4.7. Multiple 3 divided by 7 and 4 divided by 7. So now we are taking here our variance.
Why is it 3 and not 4? Why is it 3 and not 4?
Well, because it's 4 minus 1. It's degrees of freedom aliquots divided by degrees of freedom total.
Do you think that's fixed automatically if we're doing one? Well, that's really no. Do you think that's fixed automatically if we're doing one?
No, not yet, not yet. So we go step by step through it again.
Yeah. Can you close this?
Yeah, we'll go. Don't worry. Okay, so 3 divided by 7 is 0.43. 4 divided by 7 is 0.57.
Does it add up to 1 now?
Yeah.
Yes.
So here we have now the variance multiplied by 0.43 plus the variance multiplied by 0.13, which is that variance multiplied by this aliquot. We're then on this step, we're getting now this was my mistake. Brilliant. Okay. So we're getting now this pooled one down on the next level. Okay. So we're getting now, and this is now where my mistake was. This S difference is now essentially this 0.84 multiplied divided by the sample size, count of this, plus this divided by count of this. Stupid mistake. Okay. No, still not. 37, 9, that's the total. Now we're taking the square root of this. So now this is still a squared difference. Now this is now the square root of this. This is now the difference divided by L21. Okay, so now we're there. All right, good. So the mistake that I made was, so the degrees of freedom were not the problem, the proportions didn't change. The mistake I did was you come here to a pooled S squared difference, and you're aliquoting this to each of your samples by taking this pooled S squared difference divided by the sample size of a sample X, and then you take the same and you sum it up. So this equation here, and this was my thought process, I don't do this on a daily basis either. So, so we're doing this S squared difference multiplied by, or divided by the sample size of sample X, and the S squared difference divided by the sample size of sample Y. By that, we're getting to this S squared difference. This is the total standard error of the mean squared. Yes? We're dividing again because we get this variance, and we're dividing it by the sample size. So this gets us from variance to standard error of the mean.
But the actual sample size, or like not the real?
Actual sample size, yeah. The degrees of freedom are only playing a role here with the standard deviation for the aliquots. Not even for the aliquots because it's a constant. So that would have made a difference. Yep. Yes.
What's the formula for the SQL?
Which one? This one?
Yeah.
The square one? This is the sum of these two. And once you have these summed up, then you essentially are aliquoting them. You get to this S squared difference. So this is essentially, bluntly spoken, this is SCM squared X plus Y. So that's actually a different one.
So then I think my math problem is still further back. How did you get the new, like,
The aliquot?
the standard of the mean squared? I got the aliquot.
The standard error of the mean squared is here the variance multiplied by the aliquot.
Why is it the same number?
So this here is actually redundant. You wouldn't need that. That was the wrong one. Let's delete this one.
Wait, why did it repeat? No, everything just deleted. Wait, why didn't it? Yeah, somewhat.
What happened now?
Number.
No, you're fine. You're fine. You're
No,
fine.
everything just deleted. I can't.
No, don't give up. Never give up.
I'm not gonna go.
Never give up any second life.
Control V, and then it's.
Hmm?
The Elliot was Control V.
Now, hold on.
Okay, go look at the answers or it all. Like, am I never going to?
So where are you now?
Okay, right now I have variance. Yeah, I have.
You have the aliquots. You have the variances.
Mine didn't round to 0.43. It's just 0.4285. Yeah.
So are you here?
Okay. Yeah, I have that.
You have also
I have
this one.
Yeah. But once I delete SEM squared, my.
Yeah, then it goes towards 0. But if you have these two numbers, then don't delete it. Go to this point.
Yeah, I don't have those.
Yep. So now sum both up.
Wait, I have to-
Sum both variances up.
And this is- the variance is the same as the standard error of the mean, is that what you said?
The variance is not the same as the standard error of the mean. So this is,
How do you go from one to the next? Variance is standard error of the mean.
you're right. It's actually the variance. It's the variance sum.
It is, right?
Yeah, it is. You're right. You're right. Good catch. Thank you.
Oh, I was asking.
No, that was a good catch. Good catch. It's,
Yeah, I'm not getting that. Yeah.
no,
Wait. Oh, what? Variance where?
variance y and variance x. You sum it up, you get the.
Second one just said standard error of the mean. Yeah, we realized it's the same thing. Oh. So you just add the two variances and then what? Square root.
You add the variances, then you employ the square root.
Okay. Oh, I got it. Wait, so this is more simple than what we did, I think.
Yes, yes, yes.
Wait, but if you square it, it's not that number. That's it, that 0.84 is not squared. Yeah, at least not mine.
No, this is still squared. This is still squared. Here you add up the variances, you get to this pooled variance.
But why would you square it? It says it's squared.
Yeah, it is still.
Why would you square it and then take the square root? Yeah.
No, this is all still squared. This is also squared. No, this is variance. Oh, variance is not squared, you're right. Okay, next sketch. Don't worry, you're fine.
No.
It doesn't change the value.
Add the variances of x and y.
That gives you variance x and y. That's the pooled variance. Now you're going to take this variance and you divide it by the sample size of x, and you add the variance divided by the sample size of y. And that gets you to s squared difference. It's this formula. This formula here.
Can you go back to your?
Yeah.
What's L19? The variance.
That's
Variance x and y.
L19 is this one, yeah? Oh, no, this one.
Okay, so you divide the x by.
The sample size of x, and then you take this again, this pooled variance, and you divide it by the sample size of y.
And those are added or subtracted?
Added. That's the same question you asked before. It's addition.
No, but it's different.
No, that's an add. So you have L19. That's the variance x and y. That's the pooled variance.
No, I was talking about the x part. Oh my god. Oh my god, they all. Oh my god, I got it.
It works. Good.
Yeah, I worked at x squared.
Yeah.
That's subtraction, no?
No, that's added.
Oh. Okay. Sorry.
That's a plus.
Okay. So we put the spot here.
Okay. Are we all on board with this?
Yeah.
It's a little complicated. Okay. So we have now our S difference. By that, we're getting to our T by taking the difference and dividing it by the standard error of the mean.
Wait, so now the number is different. So we have to check the t-square table.
The T-score is, no, it's still significant. It's still 2.36 for degree of freedom of 7.
Oh, right. Okay.
Yeah?
Yeah.
Okay. All right.
So the 5%, we get that in the calculation. You said like to know to look at the 5% column.
For what column? You want to look at this one?
Yeah. I'm saying.
So you go for 5%, 5%, 2 tails, right?
Yeah.
And you go to degrees of freedom of 7.
Yeah.
Thank you. Degrees of freedom of 7, and here you find 2.36. That's your critical value.
Okay.
And you basically you're seeing your 2.44, your minus 2.44 in reference to your critical value, and it's exceeding this critical value. Therefore, you're rejecting the null hypothesis. And you say that wine drinkers, when they're being told that it's a $90 wine, they would rate it significantly higher. That's your insight. All right. So we're 15 more minutes. So reporting the statistics, essentially you're reporting the T, the calculated T, and the corresponding p-value. And the p-value here is reported like that. You would not, like in SAT statistics, we calculated the p-value. We don't need to do this. We can still do it. Well, we can easily do it essentially by going, and this is maybe a good exercise, by calculating the p-value. You can do easily now by using the t-test function. You remember from last time we had the t-test function. So if we go on t-test, we have now with the t-test function, and we can do now array 1, which is our $10 wine rating. Array 2 is the $90 wine rating. tails is 2, right? And the type is now, as opposed to last time we did pooled, we have now two paired sample t-test. We have a 2 sample t-test with equal variances, or 2 sample t-test with unequal variances. And this is the one we're going to be using. So this is our p-value. So this is significant with a p-value of 4%.
Wait, it's equal variance?
No, it's unequal variance. Unequal variance because the variance is a difference because it's 2 different sample sizes. Okay. That's the t-test. That's simple, right? So since we're already there, so we know now the difference is minus 1.95, right? We've calculated this by subtracting mean x from mean y, or mean y from mean x. So difference is this minus this, right? So that's minus 1.5. So now we have the standard error of the mean. Are we gonna get the lower limits now?
I have a question.
Yes.
How would you know not to do 4 minus 2.5? How would you know to not do 4 minus 2.5?
What's the definition if you have x minus y?
Oh, x and y.
Yep. You can a lot in the way. You remember last time where we did after minus before,
Yeah.
just to see that there's an increase. You could do the same here. It's like the way you want to answer the research question will determine how you're going to go about this.
Okay.
Yeah. So when you want to do a lower limit now, essentially the only thing you do, you take your difference, you subtract, just like in the same fashion, the value was 2.36, multiplied by your standard difference. This is your standard error of the mean. So your lower limit is minus 2.95. Your upper limit is the difference plus 2.36 multiplied by your standard difference. That's your upper limit. So that's how you calculate your confidence interval, which is not including the 0, which again will prompt you to automatically reject the null hypothesis. Okay? And now, in the same fashion, you can also do the effect size. You can essentially now easily say you're doing the difference divided by SQRT of your variance, right? Of your pooled standard deviation. So your effect size is 1.36.
Oh, I did not get that.
Hmm?
I did not get that. Can you say it out loud in the sentence?
So you basically so effect size is always calculated by
Oh, I see
the
that.
difference divided by the standard deviation, and the standard deviation here is your pooled variance square rooted. So the square root of your pooled variance gets you to the standard deviation again. Yeah. Yes.
I didn't get the lower limit, upper limit. Which number did you get?
Minus 2.95. So you essentially, what you do is you take the difference, you subtract 2.36 as our critical value, which is coming from here, multiplied by the standard error of the mean.
And the upper limit is plus 2.36.
Exactly. Yeah.
Yeah, do you mind doing effect size one more time?
Yes. Effect size is basically you take the pooled standard deviation or the pooled variance. You take the difference and you're dividing the difference by the square root of the pooled variance. Yeah. All right. Good. All right. So back to the slides. So we have 2.44 minus 2.44. So we just did that. We did CIs. Same story, right? We have the sample mean minus the sample difference. It's the same conversation. So we have now minus 2.365. These are the p-values. Now we have minus 2.96 and minus 0.04. We did that. So here we have the same thing. This is the standard deviation pooled. Now we have again our Cohen's t, the classification, right? Same thing. And lastly, are we so far kind of comfortable with the idea? Yeah. It's told you, spicy.
At least you joined us.
Well, I even tripped over my own calculations, right? Actually, very embarrassing.
You mess up on homework.
Well, on the homework, you have a lot of more time, right? And you're not standing in front of here and you're not calculating on the fly. So no excuses there.
Honestly, it's pretty impressive that you can do it on the fly. Yeah. And
Well,
always mess up lines, like, pretty good.
Well, I don't, this is something I don't do on a daily basis, right? I do this for teaching and I prepare for teaching, right? I go through the calculations. That's when you forget things, right? At one point. Yeah. Happens. But this is, it's also, I'm not a mathematician, I'm not a statistician, right? For me, things, I do need to prepare for each class, and I want to give you that from a more practical angle, and that's what I try to do. And yeah, sometimes stuff like that happens. And it's not something that you would do on a daily basis. If you really do statistics, you're not calculating this by hand. You won't. And you see the t-test formula, right? All these values that we have derived is usually one function in Excel. The point is just that you need to understand the underlying mathematics to employ tests correctly. And this is unfortunately what you see very often. And you see that from people working in the field, that sometimes the employment gets facilitated by understanding the mathematics, the underlying mathematics. And it's you will benefit from understanding and having done all these calculations. I believe in that. Yep. Okay, Bayesian approach to data analysis. And this is, I'm not really sure why they include this. So hypothesis testing essentially gives you a binary outcome, right? So you have either you reject it or you don't reject it. We talked about the confidence intervals as being the new statistics, as being more preferable statistics, because it takes into account the variability of things, and it takes into account a depiction and a characterization of the distribution of these differences, and not only a binary outcome, reject or not reject. So Bayesian statistics essentially go even a step further, because they take into account to what extent does my hypothesis test and my analysis change my way of thinking. And if you have a hypothesis test like this wine drinkers, but if you have these wine drinkers and you have now a certain hypothesis test, you can, based on what you have seen, you can calculate a certain probability that an individual will rate this wine higher. And you can hypothetically, you can say, okay, so based on this sample, I get this insight. But now you have a certain group of people that love wine and drink wine on a regular basis and really know how to taste wine. Then your pre-test probability of this individual rating this wine more accurately and not as high will actually be higher, because this individual would understand more about wine. So this is essentially, it's the same thing as if you would diagnose somebody with diabetes. If you test this in a population that you randomly meet on the street, you have a certain probability you pick a diabetic when you test him, right? If you do the same thing in a diabetes clinic, your probability of picking a diabetic is substantially higher.
The only reason why they're there is.
Well, yes. And the point of this is, but sometimes if somebody is well on a diabetic medication, you wouldn't test this individual as high. So only those that don't take the medication or don't respond well, they would classify as a diabetic. It's not a perfect example, but the idea is that you have a certain pretest probability and a post-test probability. And the test essentially is only informing from pre-test probability to post-test probability. So it's not showing you the entire picture. So you need to take into account your pre-test probability to come to this conditional post-test probability. And this is Bayesian statistics. And this is something right now, and they mentioned this also in the ebook like that. It's enough if you know the principle of it, pre-test, post-test, and that you take prior beliefs and prior insights into account when you do a hypothesis test. But there's a strong push in that direction to incorporate that in your thinking and in your insights and in your hypothesis, in your concluding from hypothesis tests by taking this into account. And they are quoting Kruschke, and they encourage every undergrad student to also take in graduate studies then Bayesian analysis and Bayesian statistics. So, but this is essentially what you're looking at with Bayesian statistics. You have a prior belief, and your hypothesis test informs that prior belief to come to a posterior belief after that hypothesis test, taking that prior belief into account. I think that's all that you need to know to this topic. On the quizzes, it's probably not more than that. So just a basic understanding of what it entails. Any questions on that? If not, we can conclude for today. I apologize for the mistake with the calculations. But it's good because we worked on that together. We came to the conclusion together. So it's a learning process, right? All right. Have a nice evening. See you next week for the review on Monday.
Thank you.
Thank you. Bye.